Today on Orbital Dispatch, the star that orbits a black hole every 16 years. We will break down what happened and why it matters. The star that orbits a black hole every 16 years. Open. No music. Clean start. There's a star in our galaxy moving at 7,650 kilometers per second, and it completes a full orbit around a black hole in the time it takes a child to finish school. That star is S2, and watching it move changed physics. The center of our galaxy, roughly 26,000 light-years away, is not a quiet place. Packed into a region smaller than our solar system is an object with a mass of about 4 million suns. We call it Sagittarius A, or Sgr A. And for decades, astronomers had strong reasons to think it was a supermassive black hole. But strong reasons aren't proof. Proof required something orbiting it, something they could actually track. In Section 1, what is S2? S2 is a relatively ordinary star, roughly 15 times the mass of the Sun and about 5 times hotter. On its own, it would be unremarkable. What makes it extraordinary is where it lives. S2 orbits Sgr A on a tight elliptical path. One full orbit takes just over 16 years. To put that in perspective, most stars in our galaxy take hundreds of millions of years to complete a single trip around the Galactic Centre. S2 does it in the time between a child starting primary school and finishing their A-levels. Astronomers first began tracking stars near Sgr A in the early 1990s, using infrared telescopes powerful enough to peer through the dust clouds between us and the galactic core. S2 quickly became the most useful of them all. In Section 2, how close does it get? S2's orbit is not a circle. It's a stretched ellipse, and at its closest point, called pericenter, it passes within roughly 120 astronomical units of Sgr A. That's about 3 times the distance from the Sun to Pluto. In galactic terms, that is extraordinarily close to a 4 million solar mass black hole. It was at that closest approach, in 2018, that S2 hit its peak speed, 7,650 kilometers per second. That's approximately 2.5% of the speed of light. In Section 3, why that speed matters. 2.5% might sound modest. It isn't. At that velocity, you could travel from London to New York in roughly half a millisecond. S2 is moving fast enough that the effects of general relativity become measurable. Not theoretical, not modeled, but directly observed. 2 effects in particular were confirmed during S2's 2018 pericenter pass. The first was gravitational redshift. Light from S2 was stretched to longer wavelengths as it climbed out of the intense gravitational field of Sgr A. This is a direct prediction of Einstein's general theory of relativity, and S2 confirmed it right there in the Galactic Centre. The second was the Schwarzschild precession, the slow rotation of the orbit's closest point over successive passes, which was confirmed using S2's data in 2020. These aren't small corrections. They're evidence that general relativity holds, even in one of the most extreme gravitational environments we can observe. And crucially, S2's motion gave us the most precise measurement yet of Sgr A's mass, pinning it down to approximately 4.15 million solar masses, the closer. S2 isn't a special star. It just happens to be in the right place for us to learn something extraordinary. 16 years, 7,650 kilometers per second. And in that motion, a confirmation that Einstein's equations still hold in some of the most extreme conditions our galaxy has to offer. The next pericenter pass is expected around 2034. Astronomers will be watching. Outro, calm, direct. If you found this useful, subscribing helps the channel keep making these. There's more in the series on black holes and the Galactic Centre. Links are below. Main takeaway: the evidence is still evolving. Subscribe to Orbital Dispatch. Next, our next breakdown.